This is Physics 1 course. In this video I will teach Newton's second law. Newton's second law is basically F, which is the force applied to an object, equals the time derivative of the momentum of the object, dt. Now what is momentum? It's very simple. Momentum, P, is defined as mass of the object times its velocity. So here is the momentum, the definition of momentum. Here is the second law of Newton. Now I should mention that the second law of Newton is only valid in an inertial reference frame. So I just wrote this statement here to make sure that you memorize it. Now I'm going to solve a couple of examples to show what these things mean. Let's say I am sitting on a box. So I am sitting on a box, and the box is being pulled by a force, like by a rope. So it's a rope here that is pulling me. Now I see a ball that is moving. So it's moving somewhere. So its velocity is in this direction. I also know that the ball is under the force of gravity. So it's being pulled toward the earth. So there is a force. And the magnitude and the direction of the force is known to me. So can I write this equation from the reference frame that is attached to me? Like if this is x and y, can I solve this problem in this reference frame? No. Why? Because the force that is being applied to me according to the first law of Newton is making my reference frame a non-inertial reference frame. Therefore, I cannot solve this problem using this equation in this reference frame. So what I can do, I can go stand on the surface of the ground. So this is the ground. So I should go stand here such that there is no other force applied to me, or the net force on me is zero, because I am being pulled by gravity, but I am also being pushed upward by the ground, and the two it's usually called normal force, and the normal force and the force of gravity on me in that case will be zero. So the net force is zero according to the first law of Newton. Now I am sitting on an inertial frame. So if now I define y and x, then this is an inertial frame. Then I can use the second law to solve this problem. For most of the problems that we are going to deal with, the mass does not change during its motion. Like the mass of the ball doesn't move in its motion. Therefore, the mass can be taken out of the derivative. So for most of these cases, therefore, I can write F, the force, equals mass dV dt. And you just need to remember the previous videos where I defined this as the acceleration. So it's m times a. But remember, F equals ma is not exactly Newton's second law. It is only valid if mass of the object does not change. So let me quickly give you an example when the mass changes. Let's say there is a truck. So it has some wheels, and there are some like soil in the truck. So there is a hole here, and the soil is leaking out. So the soil is, and the mass of the soil in the truck is being reduced because of the hole. So therefore, in that case, I have to go back to the original exact form of the Newton's second law. I can't use this because m is now a function of time. So the time derivative will be applied on the mass as well. But for this problem, that the object has a constant mass in the motion, then the mass is constant. I can use this equation. Now let's use the Newton's second law to solve a couple of problems such that we are well familiar and comfortable with this law and how to use it. So a body of mass 200 kilograms is at rest on a frozen lake. Friction is 0. So let's say I have a frozen lake. So this is the surface of the ground, and the surface is frozen such that friction is 0, and there is a body, let's say a box, that has mass of 200 kilograms, and it is at rest. That means V naught is equal to 0. The body is pulled by a rope with a constant force of 100 newtons. So there is a force equals 100 newtons. So you may want to know newtons is the unit of the force. Find the velocity of the body when it is moved for 20 meters. So let's say this is still the ground. Let's say box is finally 20 meters away. So this is the same box. It is pulled for 20 meters. So that means this distance is 20 meters. So mass is still 200 kilograms. Okay, I wish we had used a different symbol, because we are now using m for meters and also mass, but please just note that this is the unit, that is the symbol. So anyways, this is 20 meters. Now I want V. What is V here? So remember we had this equation, we derived it in the previous video or videos. V naught square equals A. So we basically need A, x minus x naught. So x minus x naught, if I assume that this is my reference frame, y, x, it is attached to the ground, not to the body. So it stays here. Note that the net force on the ground is almost 0. So basically the only force being applied to the earth is coming from the sun, but in this problem that force is nearly 0, negligible. So therefore I can assume that my reference frame is almost an inertial frame. So I can use the Newton's second law in this reference frame. Now remember, when I had a vector equation, I could always write it in its component forms, and fx is equal to max, fy is equal to may, and fz is equal to maz. So now in this case the force is in x direction, therefore I have fx. This is fx, not fy, not fz. It's fx, and this is actually ax. So ax, according to this equation, equals fx divided by m, and fx is 100 newtons, and mass is 200 kilograms. 200 kilograms. So therefore AX is 0.5 newtons per kilograms. Or if I use this equation, it's equal to 0.5 kilograms meters per second square, and a kilogram here. So now the kilograms cancel out. It's actually 0.5 meters per second square, as always. Now let's insert everything into this equation. Half V I don't know, I need to find that, but I know V naught is 0, equals AX is 0.5 meters per second square, and X minus X naught. So if this is X naught, which is 0, this is X, which is 20 meters. So it's 20 meters. So it is equal to 10 times 0.5 is 5 times 2, 10 meters square second square. So now therefore V square equals 2 comes up here, 20 meters square seconds square. Therefore V equals the square root of 20 meters per second. I will solve a couple of more examples and problems in the following videos, such that we become quite familiar with the second law of Newton and how to use it in physical problems. Thanks for watching. Please subscribe to support my channel. If you have any question or comment, please send me an email at open.physics.project@gmail.com. Thank you.